like getting sun blindness with that. The second thing, though, remember, is that there's something called the Rayleigh criterion that states that the larger the aperture, the better it is able to resolve small details, right? So big telescopes can resolve smaller details. That's what's going on here. With the large telescope, these things that up until now had been these fuzzy spiral nebulas with 30-inch telescopes, 16-inch telescopes, right? 100 inches, suddenly you've got better angular resolution. You go, okay, that's a star, that's another star. In between, there's not a star. These are stars. Look at the Andromeda galaxy. There's individual stars, right? Okay. But at Mount Wilson, he's not. I guess you can look at the Andromeda. You can't look at the large and small Magellanic Clouds. So he finds Cepheid stars, right? He calculates the distance to the stars using their brightness-distance relationship, and he calculates the recession velocity of many galaxies, right? There's a relationship. I don't know if you can see it here, right? No. This is what we call a straight line, right? Now, of course, we've picked, this is sort of some hand-picked stuff. It's pretty messy. It's actually pretty messy to get, you know, the Hubble data for this because galaxies orbit each other, right? So you might pick a galaxy from a local group that has a recession velocity away from us, but it might have an orbital velocity toward us, yeah? And therefore fall below this line or be moving away from us in its orbital trajectory. So this is devilishly hard data to get. For sure, I'm guessing that this is, you know, kind of hand-picked stuff here. And that's why the Hubble constant, you know, is just like, well, you know, it's about this, right? You know, because it's pretty approximate, okay? So the greater the distance, the greater the recession velocity. And then, you know, why is that? Do we know why that is? Why is everything moving away from us? It's afraid. We have BO. Here, let's go back to the one-dimensional universe because I can understand that. Okay, here are these red dots are galaxies, let's say, right? Okay, let's pick, we're one of these, right? Wish I had three hands. We're that galaxy, yes? Okay, now I'm going to stretch this universe. Watch, notice that every galaxy, every other red dot is going to move away from us, yes? Okay, do you see that the ones that are farther from us are moving away faster? Aren't they? The ones closer are moving more slowly. This is what happens when you stretch something, right? It's this exact linear relationship, you know? This is a thing, right? We think about this with climbing ropes because if you have a cliff and you have your anchors, you know, here, tree, right? You have your anchor here and you're belaying from here, and somebody takes a catastrophic fall, right? And the rope stretches 10 feet, and you're halfway down the rope. You're going to stretch 5 feet. Are you 5 feet to the edge? That could be pretty exciting, couldn't it? Yeah, if somebody takes a catastrophic fall on a rope where you've got a long anchor, right? These ropes are designed to be like rubber bands, because if they're not, you die, right? You hit the end of your harness and bam, it stops you, right? Oh, you die. Okay, so these things are, you know, the climbing ropes are called dynamic ropes. They're designed to stretch like that. And so, you know, we were talking about that last night. So, yeah, there it is. Okay, now the second thing is I want you to try another exercise because I want you to pick a different dot. So let's pick, you know, this dot or this dot, right? Is everything moving from the dot you just now picked? Yeah, every other dot is moving, and anywhere in the universe that you are, you're going to observe exactly the same thing. So it's not like we're in a special place at the center where everything's moving away from us. Every observer in an expanding universe sees exactly the same thing. Everybody moving away from them at a rate that is proportional to the distance that they are from you. Yeah? Well, I was going to point that out, but I don't want to be a smart ass in my little climbing class. The convention, I would think you'd want to use a static rope. But then, you know, of course, then the beauty of using just one rope is there's two beauties, right? Just back yourself off the cliff, right? And use a dynamic rope, and then it really makes the fall factor much, much smaller, right? Fall factor is how far you fall before you hit the rope divided by the length of the rope. The smaller that is, the less jarring it is. So it's actually a good thing. The second thing, the second reality is that I don't think we're going to be really falling that far, and we're going to be belaying pretty tight, right? So basically, if somebody falls, they're going to fall 2 feet onto the rope, and the rope will be 80 feet long with a, you know, Right. A 0.025 fall factor, right? Okay. So this is our formula. Our new formula is and this is the Hubble expansion one. Is that the recession velocity is Hubble's constant. That's Edwin Hubble's last name, Hubble. Starts with an H, yeah? Right? Yeah? Hubble? Okay. Edwin Hubble. Okay, times the distance. And then notice that this distance is in megaparsecs. Mega parsecs. Wow! That's a long way, isn't it? A megaparsec is a long way. That is 3.26 times 10 to the 6th light years, right? Yeah? That is 1 times 10 to the 6th parsecs. Yeah? Wow, that's a lot. That's a long way, and that's because it's pretty subtle, right? You got to get pretty far away for this. So if you go a megaparsec from us, you're going to be moving 71 kilometers per second away from us. If you go 2 million parsecs from us, okay, you're going to be going 142 kilometers per second or thereabout from us, depending on whether you're orbiting, right? Remember, the group velocities for galaxies are on the order of kilometers per second, right? So this is, to tease this data out of the background motion of stars, right? And this is plus or minus 2 kilometers per second. And how we know this, we'll talk about later, but we know this fairly well, right? Okay. Okay, MPC is megaparsecs. Whoa. So this is 71 kilometers per second per megaparsec of distance, plus or minus 2. So what is the distance to a galaxy? Let's just be Edwin Hubble, right? You do spectroscopy. There's a line that should be 480 nanometers. It's coming in at 497 nanometers, yeah? Yeah? Okay. And so how far away is it if we use Hubble's law? This is, by the way, a bad way to find the distance to it, but sometimes you can do it this way, right? Okay. So the first thing I'm going to do is I'm going to use this relationship here and find our recession velocity, right? So it looks to me like our delta is 17 and the original is 480. That's going to be V over 3E5. And again, I'm doing the speed of light in kilometers per second because Hubble laws are done in kilometers per second, right? So 17 4/80ths. Whoa, got to put divide in there. This is, the recession velocity is 1.0625 times 10 to the 4th kilometers per second. And I'm not going to round to sig figs because I'm not done with the problem yet, right? Okay. So now this is part 1. Part 2 is that V is HD, right? So D is V over H. Yeah? So that's 1.0625 E4 kilometers per second divided by 71 kilometers per second per megaparsec. Right, so our answer is going to be in what units?
Megaparsec.
And we get a mere 149.6 megaparsecs. Yeah, just about 150 megaparsecs or so from here, Give or take, kind of a lot. Lots of fun we can have with this, huh? So let's try this. This is just simple. This doesn't have the redshift question in there. She's got the... But Spencer, I think to answer your question why they don't do a static anchor is that it's pretty foolproof if you're anchoring to the same rope, right? Whereas if you've got a static line, then you have 2 ropes, and beginners might not connect the 2 ropes. Whoops. So when somebody falls, they go, off the cliff, right?